sixth session where we are going to discuss about the dynamic programming. Probably you can recollect last session we were talking about greedy approach. So, we were discussing about the minimum spanning tree and Dijkstra's shortest path algorithm. So, probably you can recollect we were discussing about the fundamentals of greedy approach. I told you that greedy approach has got three procedures. One is the selection check, second is the feasibility check, and third is the solution check. And as part of that we had discussed about so many problems in the last two sessions. Last session we discussed about the minimum spanning tree and Dijkstra's shortest path algorithm. So, let us recollect some of these things. So, last class we discussed about the spanning tree. So, I was telling you that a spanning tree of a graph is a tree that is it does not contain any cycles and it spans all the vertices, and I was telling you that a minimum spanning tree is a spanning tree on a weighted graph that has a minimum total weight. So, you can see this example. So, this is what we were discussing in the last session. So, we have taken a graph and we had seen that a graph has got vertices and edges, and I was telling you that there are two algorithms that are available for finding the minimum spanning tree. The first algorithm is called the Kruskal algorithm. So, we have seen that we have to sort all the edges, and this is how it looks like, and I was telling you that we have to take each and every edge and then we have to add that to the resultant if it is of minimum cost. So, you can see very well the edges 1, 2 is added, then 3, 6 is added, 4, 6 is added, 2, 6 is also added, but 1, 4 cannot be added because if I connect these two, this will become a cycle that violates the fundamental principles of the minimum spanning tree. So, this has to be rejected. So, last class we discussed about how to write algorithms for Kruskal algorithm, etc. This is another example. Again you can see very well we are sorting out all the edges and then we keep on connecting to the resultant if it is minimum and if it does not form a cycle. So, you can see very well. So, this is the resultant minimum spanning tree that is being obtained from the original graph. So, this is another algorithm. So, this also we discussed as the Prim's algorithm. So, you can see here the approach is something similar to your Kruskal algorithm, but the difference is that in Kruskal algorithm everything is sorted and then added one by one, but whereas here we are finding the minimum edge. So, that is 1, 2. So, that means now 1 is available, 2 is available. So, all these edges that are having this as a starting vertex will be considered. So, that means now 2, 6 is going to be the next minimum cost edge. So, that will be added. So, in this particular manner we keep on adding that into the resultant. So, I was telling you that in this particular manner we can find the minimum spanning tree. Last class we also discussed about the Dijkstra's shortest path algorithm. So, I was telling you that Dijkstra's algorithm was based on the concept of relaxing. So, this is the case of the relaxing procedure. Suppose if d of v is greater than d of u plus w of u comma v prior to the relaxation. So, the edges will be relaxed like this, and I was telling you that if d of v is going to be less than or equal to d of u plus w of u comma v before the relaxation step. So, we will not alter anything, this will remain as it is. So, this example we discussed in the last class. So, please recollect, we have taken the edges and our aim is to find the shortest path from the starting vertex to the end vertex. So, the concept we discussed in the last class is that initially we are starting with the solution set which is going to be null, and then we are checking out for the minimum cost edge. So, you can see very well the subsequent stages becomes like this: C is minimum, therefore, C is added to the resultant set. So, now A is available, then C is available. So, we can proceed to the next step. So, now you can see very well some of the calculations are being redone. So, now you can see very well the cost of A to B is 10, but since now C is available, we can take a route something like A to C and then C to B. So, like that some of the cost can be recomputed. So, again we have to choose the minimum. So, you can see very well one by one all the nodes are added to the resultant. So, you can see that this is what we discussed in the last session, and we discussed about how to write algorithm for all the things. So, if we summarize the greedy approach that we have been discussing all along, you can see that greedy approach has got some finest properties where we are using that to find the optimal solution for most of the problems. So, if you take the essential points, you can see this particular slide. So, a greedy algorithm makes a sequence of choices. Each of the choice that seems best at the moment is chosen. So, this is what we had seen, that is local optimal property, and these are the two ingredients that all the algorithms of greedy approach resemble. One is the greedy choice property and another is optimal substructure. So, greedy choice property is what we had been seeing as the local optimal decision. I was telling you a layman story that as a greedy man, we are assessing all the decisions and then we are choosing a decision that is optimal at the present moment. So, I was telling you that for many problems this approach would work. So, we are making choice that seems to be best at the present moment, and then we are trying to solve the sub problems. And the choice that is made by the greedy algorithm may depend on the choices that have been taken so far, but it cannot depend on any future choices or solution to these sub problems. In other words, this sort of greedy algorithm is a short term decision making mechanisms. So, we are going to solve everything in the top down fashion only, and normally if you take some problems, normally the greedy approach yields a global optimal solutions. And by optimal substructure means, we mean that suppose if an optimal solution has been obtained for the problem, then the solutions to the sub problems are also optimal. If we can prove that, it is what we call as the optimal substructures. I can give you a layman example, that is, say for example, if the distance A to C via B is optimal, then the path between A to B and B to C should be optimal. So, that is what we mean by the optimal substructures. So, you can see this example where these two properties are clearly present. So, you can see this graph, and we call this as a multi-stage graph. See, the problem is to find the shortest path from S to T. So, you can see, so I am here. So, 3 choices are available to me, one is 1 and then 3 and then 5. I have to choose a minimum is 1, therefore, I am going from here to here using this particular edge, and then from here I am using this, and then from B I have 2 choices, I am choosing the best, that is going to be 5. So, the shortest path from S to T is nothing but 1 plus 2 plus 5, this is equal to 8. So, if you take this particular problem, you can see the shortest path is coming effectively, right. But if you take some other multi-stage problems, this greedy approach may not work. So, before proceeding further, let me give the definition of a multi-stage graph. A multi-stage graph G is equal to V comma E is a directed graph in which the vertices are partitioned into k is greater than or equal to disjoint sets V I, where I is between 1 to k. So, you can take this particular example. This is a case of a multi-stage graph. So, this is one stage, this is another stage, this is another stage, this is another stage. So, this is the first vertex. So, we call this as a source, and this is the final vertex which we are going to call as a sink. So, the multi-stage graph is like that only. So, the graph you can see very well is partitioned into various disjoint sets. In the graph that I had shown, we had seen that the vertices are partitioned into 4 stages. Your source is one stage and your destination is one stage, and remaining is arranged in 2 stages. And also you can note down one property, that is the edge u comma v connects 2 stages. So, in this particular example you can see, if I choose a edge, you can see very well this connects this stage and this stage. So, whatever the edges you take, it connects 2 stages. For example, you do not have any edge going from here to here, it can't be possible, because as a definition the edges means it has to go from one place to one stage to another stage only, right. So, suppose if you take this particular problem, if I want to find the shortest path from the first vertex, this is called the source, and the final vertex, this is called the destination. If I want to find the shortest path from here to here, if you apply the greedy approach, you can see very well we encounter a problem. So, let us see how this works. I am here, so only 3 choices are available to me. So, that is 1, 2 and then 5. So, the minimum is 1. So, I am taking a route from S to A. So, now I am here. So, that means now 2 choices are available to me, one is 4 and another is 11. So, the minimum is 4, therefore, I am picking the path from A to D, and unfortunately what happens now is that the path between D and T is what you say is having a weight of 18, therefore, the shortest path becomes 1 plus 4 plus 18. So, that means it is going to be 23. But unfortunately, this solution is not a global optimal solution, because the real short path comes in this particular manner. It is from S to C, that is 5, then C to F, that is 2, then F to T, that is going to be 2. Therefore, the best path is this one, S to C, C to F and F to C. So, you can see now that the global optimal value is going to be 9, but unfortunately my greedy approach gives me a value of 23. What is the problem with this? The problem with the greedy approach is, as I said earlier, all the decisions are locally optimal and it is a short term decisions. So, that is the reason why I am not able to foresee that the path between D and T will be having more weight. I can give you a layman example also. Let us assume that there are 3 roads available, you have a choice. So, one route that appears to be very effective because there is no traffic. So, you are taking that particular road, you go to another destination and from there the road between that intermediate place and your destination becomes too crowded. So, what appeared as rosy earlier is no longer a effective or optimal solutions. So, this is the greatest problem of a greedy approach, and because of these particular reasons sometimes the greedy approach will not work, and sometimes the optimal substructure also may not work, in the sense that sometimes what seems to be a good solution for the original problem, suppose if it could prove that for suboptimal solutions, if it is not the case, then again problems will come. For example, greedy approach for the shortest path algorithm will not give much problem, but whereas for the longest problem this may cause lots of problems. Okay. So, this is the case of the greedy approach. That is the reason why we are focusing to the next design technique called dynamic programming. Dynamic programming is a very effective technique that has been applied to optimization problems like greedy approach, but optimization is more effective in dynamic programming because it is taking a long term view of everything and then it tries to take a decision that is of long term nature. In other words, for the same problem of multi-stage graph, the solution procedure would be totally different. What we will try to do as part of dynamic programming is that we try to see till the end and then we choose a decision only if it seems to be very effective. So, this problem was designed by Richard Bellman in 1950s actually to solve optimization problem, and here by programming we mean planning. So, we do not do any actual programming here. What we are trying to do here is that we are trying to take decisions based on the long term. So, the main idea of dynamic programming is like this, again like a divide and conquer strategy. So, we try to divide the problem into lots of sub problems, and many problems will be overlapping in nature. So, the main idea is we try to solve several smaller problems and then we are going to record all the solutions in a table, and then we are going to manipulate that particular table and then we will try to construct a solution from that particular table. So, this is what we are going to do as part of this. Dynamic programming is a very famous technique, and the research have proven that the solutions that are generated by the dynamic programming are always very effective, and many times the optimal solutions are obtained by the dynamic programming rather than the greedy approach. Many problems can be solved by the dynamic programming, and some of the problems that are given in your syllabus are computing binomial coefficients, then Warshall's algorithm for transitive closure. This problem is very important for the next algorithm, that is the Floyd's algorithm for finding the shortest path of a particular graph. So, in greedy approach we discussed about Dijkstra's shortest path algorithm. It is called single source shortest path algorithm. That is, if we have a starting vertex and then the final vertex, the shortest path algorithm will find the path from the initial stage to the final stage. But whereas the Floyd's algorithm is a all pair shortest path algorithm, where we will try to find path between any vertex and any other vertex. And dynamic programming is found to be very useful for the optimal binary search problem also. And then we can also use dynamic programming to solve various discrete problems like knapsack, etc. So, the domain of dynamic programming is mostly optimization problems only, and the strategy again is to solve the optimization problem by combining the solutions to the subproblems. So, the strategy is like this: a set of choices must be made, like greedy approach. Here also the problem solution involves multiple decisions. So, we have to take every decision at a time, and as choices are made, subproblems of the same form arises very frequently. The key is to store all the solutions of the subproblem in a table, so that can be reused in the future. You may ask me a question like this: sir, here also the approach seems to be like taking a problem, dividing that into lot of subproblems, and then we are trying to solve those subproblems, and then we are trying to combine everything to get a global optimal solution. Is it not looking like a divide and conquer strategy? Fine. There are certain subtle differences exist between the divide and conquer and the dynamic programming. So, even though we do the same thing as partitioning, solving and combining of your things, the differences do exist. That is, here you can see problems are independent. So, we solve the subproblems independently and recursively. Here you can see the subproblems are dependent, that is, the subproblems share subproblems. Every subproblem is solved just only once. So, here in dynamic programming we are solving the subproblem only once, and the solutions are stored in the table, and that is used for the highest levels. So, the difference is in top down approach of divide and conquer, what we are trying to do is we are trying to divide the problem into lot of subproblems, and then we are trying to solve all the problems, and then we are trying to combine. But whereas in dynamic programming the approach is bottom up. So, here we are trying to divide the problem into lot of subproblems, and most of the problems are overlapping in nature. So, we try to solve everything, and then we are keeping that in the table. Why? What is the reason for that? The reason is whenever we encounter a subproblem, so again we do not have to start from the scratch, and we may look into the table and we can use the existing value of the table, and then we can reuse that to find the answer for the current subproblem. So, here you can see the differences between dynamic programming and also greedy approach is listed here. So, you can see very well again the difference between the dynamic programming and greedy approach is dynamic programming uses the optimal substructure in a bottom up fashion, and again the difference is in greedy approach you take the short term decision, but whereas in dynamic programming you are taking a longer view of everything. In other words, you can see very well the dynamic programming is a brand new strategy that has got some differences with both divide and conquer as well as your greedy approach. That is the reason why we are taking this as a separate paradigm of solving the problems, right. And the fundamental philosophy of dynamic programming is called as the principle of optimality. The principle of optimality is, you can see here, is the property that whatever the initial state and decisions are, the remaining decisions must constitute an optimal decision sequence with regard to the state resulting from the first decisions. So, here the important points are this one: whatever the initial state and decisions are, so that is irrespective of your initial state decisions, the remaining decisions must constitute an optimal decision sequence with regard to the state resulting from the first decisions. For example, I can give you a layman example for this. Suppose if you say that the path between A to C via B is optimal, then according to the dynamic programming, then the path from A to B is optimal and the path from B to C is optimal. Therefore, the path between A to C is optimal. So, that is what the principle of optimality conveys. In other words, it is something like this. Suppose if you take a decision and if you call that as optimal, then you try to divide that decision into lot of sub decisions, then by the principle of optimality all the sub decisions should be optimal. That is the reason why we are saying that the path between A to C via B is optimal, then the path A to B and B to C should be optimal. The corollary also applies. Suppose if you have two decisions and if you call those decisions as optimal decision, then if you combine that, then that also should constitute only the optimal solutions. That is the reason why dynamic programming have become so powerful. And another thing that you can note down is that in greedy approach you will have only one decision sequence that is generated, but whereas in dynamic programming you will get plenty of decision sequences. So, you will have all possible optimal solutions and out of that you can pick up the best solution for the given problem. You can see that is the reason why we are approaching dynamic programming with these regards. Most of the solutions are expressed in a recursive manner. We are trying to solve the problems and then we are trying to store everything and we are trying to construct an solution out of that. So, you can see very well these are the three components your dynamic programming should have. Like we had seen in greedy approach, the three components are we have seen is selection procedure, then feasibility check and a solution check. Here also you can see these three basic components will be there. One is the recurrence equation, second is the table, third is a backtracking procedure for delivering the optimal solutions. These three procedures will be there. So, you can see very well the dynamic programming for a given problem can be written using these sequences. The first one is characterize the structure of an optimal solution. This is very important. So, the first step everyone should do is you should take a problem and then try to visualize that problem as some set of decisions and try to write the recursive equation of that particular thing. This is the most challenging part, and if this is done, then most of the problems are solved. So, the first step is try to visualize your problem as a set of sub decisions. Second is recursively define this. So, try to formulate equations, then compute the value of an optimal solution in a bottom up fashion, then construct an optimal solution from the computed information. So, in other words, these are the 4 steps every dynamic programming should take. So, try to visualize, then try to code that as a form of a recursive equation, then try to solve all the sub problems and store it in the tabular manner, and the final thing is try to generate an optimal sequence from that stored value. In other words, if you say that these components are present in an algorithm, we can call that as an algorithm that represents the dynamic programming approach. So, these are the steps. So, if you try to formulate the rules for it, the first rule is principle of optimality. No program which violates the principle of optimality can be considered as an dynamic programming. So, rule number 1 is this thing. Second thing is overlapping sub problems. When you are trying to divide your problems into a lot of sub problems, sometimes the problem may be repeated in many ways, and you should not attempt to solve that like your divide and conquer. So, you use something called a memoization algorithm. So, that means you try to solve your subproblem only once and store it in the table, so that you can also reduce the amount of memory that is required for solving this particular problem. So, the method of storing that in a table and reusing the value of the table for the final solution is one of the hallmark characteristic of the dynamic programming. This is rule number 2. Rule number 3 is bottom up fashions. So, greedy approach and divide and conquer algorithms are all top down design approaches. They start from the top, but whereas here we are going from bottom up fashion. In other words, these are the 3 rules that you have to look for in solving the problems if you decide that your approach is going to be based on your dynamic programming. The students, I can give a strong advice that dynamic programming is most apt for solving many problems, and I always recommend this as a solution strategy, because you can give some guarantee that your programs will always yield optimal solutions. In the case of divide and conquer, that can't be said, because optimization is not the domain, natural domain of your divide and conquer. similarly, for greedy approach we cannot give that suggestion, because for some problem it seems to work, and there are certain situations where the greedy approach may fail also. So, compared to these strategies, you can always claim that your dynamic programming is always better. So, now I can give a small example to understand how dynamic programming can be implemented. So, here you can see very well, this is an example of a Fibonacci series. So, you can see very well the algorithm looks like this: function f of n, if n is equal to 0, output is 0, if n is equal to 1, output 1, else output is f of n minus 1 plus f of n minus 2. If you try to solve this problem in a top down manner, you can see the conventional algorithm will start generating this sequence like this. It will try to start generating the sequence, and if you try to draw a recursive tree, you can see the tree will look something like this. If you see this particular example, you can see there are many problems that are overlapping. That is, if I want to solve the Fibonacci of 10, it is going to be Fibonacci of 8 and Fibonacci of 9, and if I want to calculate the Fibonacci of 9, again it is going to be the Fibonacci of the lower terms. So, if you see carefully, many problems are overlapping. You can see this slide. If you try to draw a slide, you can see there are many overlappings. So, you can avoid this overlappings. You can see lots of overlapping are there. This is what we call as the overlapping subproblems. So, to avoid that, the dynamic programming approach will try to assume that, fine, what is the need for calculating again and again? Why can't we store everything into a table? So, the advantage is, suppose if a value is required, all I can have is the value of the previous two things, and if I able to find that, I can find the sum of that. In other words, you can see very well, the greatest advantage of dynamic programming is lot of space is being saved. So, that is the greatest advantage. So, your solution to Fibonacci problem using dynamic programming will be an approach like this. So, bottom to top values are stored, and the greatest advantage is this reduces the repetitive calculations. So, now we will try to enlarge our scope, and then we will try to cover the problems that are given in your syllabus. In your syllabus, the problems that are given are multi-stage graphs, all pair shortest path algorithms, then optimal binary search tree, and then the traveling salesperson problem. So, just now we had seen the discussion of the multi-stage graph. So, we had seen some examples of multi-stage graph also. So, we had seen that the multi-stage graph is nothing but a graph having vertices V and E, and we had seen that these are partitioned into disjoint sets, and also we had seen that the edges will connect between two stages, and the first starting vertex is called the source and the finishing vertex is called sink. So, we had seen this already. So, now what we are going to do is, we are going to find the shortest path or the minimum cost path from the source to sink. So, for this reason only we are going to use the dynamic programming now. So, we will have a small break, and after that we will resume, and then we will try to solve this problem using the dynamic programming approach. I welcome you back to the session. Actually, we were talking about the dynamic programming and its effectiveness. So, we also started the multi-stage problems. So, now we will try to see how we can solve this problem. So, the multi-stage problem is to find the minimum cost path from the source to sink, and for this dynamic programming is used mostly. So, this example we had seen just now, I told you that this is a multi-stage graph because the vertices are divided into a lot of disjoint partition. This is one stage, this is next stage, this is another stage, and you take any edge that connects between vertices of two stages. So, we had seen that the greedy approach will not give correct answer because I told you that since the decision is an local optimal decisions, I will take the root of 1 because this seems to be very effective, but unfortunately after that it becomes too complex. Because of that we are getting an answer of 23, and also we had seen that the actual path is only 9. So, that is the reason why we are going for the dynamic programming. So, now you can see the disadvantage of the greedy approach, that is we are taking an immediate decision, that is a problem. Had I waited till this is known, probably I would not have made this decision of going rashly from S to A. So, the philosophy of dynamic programming is to wait till the end to see which is very effective, and then we will take decisions. So, we use two kinds of algorithm to solve this problem in dynamic programming. The first approach is called the forward approach. So, here you can see the problem is I have to find the minimum cost path from S to T. So, I am formulating this problem now like this, you can see very well. It is going to be three choices: choice of going here to here, that is 1, plus going from A to T. So, this is quoted as D of A comma T. So, for your convenience this diagram is redrawn like this. So, I am going from S to A, and then after that it becomes a problem of finding some path somehow to reach your destination T. Similarly, 2 plus D of B comma T and 5 plus D of C comma T. So, the best path is a path that gives you the minimum, but unfortunately you can see very well what is the distance between A to T. This can't be taken in a single stroke because now you have two possibilities. From A I can go to D, and then from D I can come to T. Other thing is from A to E and then E to T. So, now you can see very well D of A comma T becomes minimum of 4 plus D distance of D comma T plus 11 plus D of E comma T. So, if you take the minimum, you can see very well it is going to be 22. So, I cannot take this decision at all unless I find the values of all these things. So, D of A comma T I am finding it is going to be 22. Now, I will concentrate on this, that is what is the distance from moving from B to T. So, you can see very well this problem B to T becomes like this. It becomes 9 plus cost of moving from D to T then 5 plus distance between E and T, and you can see one more possibility is 16 plus cost of moving from here to here. Okay. So, if you see, it is going to be 9 plus distance between D to T. This is not a sub problem because this can be directly obtained from the graph. So, D to T is 18, 5 plus 13, then 16 plus 2. So, it is going to be 18. So, the minimum is, you can see very well, it is going to be 18 only. So, that is what your D of B comma T is all about. Then let us try to see what is D of C comma T. Only one possibility is the distance between C to F and then F to T. So, it is going to be 2 plus 2 equal to 4. Now, you can see very well your problem of S to T, which became later on as the minimum of 1 plus A comma T, 2 plus B comma T and 5 plus C comma T now can be easily solved, because now we know the values of D of B comma T, D of C comma T. So, now you can see everything, you can substitute everything, and the minimum is 9. This is the difference between your greedy approach and dynamic programming. So, this approach is called the forward approach, and the kind of reasoning we are making is called backward reasoning, because from the sink we are finding out all the things. The algorithm can be written easily like this: algorithm, forward approach. You can see the parameters are G, K, N, P. K represents the number of stages, graph G of V comma E, and N is nothing but the number of vertices that is present in the graph. E is the set of edges, and C of I comma j is going to be the cost of I comma j, and then we are using an extra parameter of P, which is going to record the minimum cost path. So, the algorithm starts like this: cost of n is going to be 0. Initially the cost is 0, and you can see very well the problem starts from here. We are trying to see the problem in the backward manner. So, that is the reason why we are calling this as the backward reasoning. So, you can see the loop becomes n minus 1 to 1. Okay. So, we have stages starting from 0, therefore, we are coming from the right to left. So, the loop becomes n minus 1 to 1, step minus 1 do. So, we are choosing a vertex, and if we call that vertex as R, and we are choosing that vertex such that j comma R is an edge of G, and C of j comma R plus cost R is minimum. You can see in the previous example, you can see like this. It is, in this particular case, you can see it is going to be 4 plus cost of d to t. This is one option. Another option is 11 plus 13. So, you can see very well we are choosing the minimum, and we are going to the path that is dictated by this minimum. That is what we are trying to write here as code. So, we are trying to find which path is minimum, and then we are trying to update your cost, and then we are also recording the vertex that gave you the minimum, because using this your solution can be easily generated. And we are going to store the data about the path also. Path you can see very well can be easily obtained, that is the path is your source, your end stage is nothing but your sink. So, you are going from 2 to k minus 1 and then you are finding your path p of j as d of p of j minus 1. So, if you take this particular example, you can see very well the minimum is going to be d of c comma t, because you can see very well in this sentence d of s comma t, if you take all the minimum, you can see very well the minimum is going to be 9. And what vertex gave you the minimum, what decision made you to get this minimum? The decision is d of c comma t. Therefore, now I can conclude that I have to choose this particular path only. Okay. And from C, the path between C and D is via only F. Therefore, my shortest path or the minimum cost path is between S to C, C to F and F to T. So, the advantage of storing the path or the k that gave you the minimum is that using that particular k, you can always what you say trace the minimum cost path, that is the greatest advantage. So, you can see very well the algorithm works in two stages. In the first stage, you can see very well it tries to find what you say the cost of the shortest path. Then in the second phase, we are trying to identify the k that gave you the minimum, and based on that the path can be constructed. And here you can see implicitly the table is also used. For example, every time we are not going to calculate the values, and whenever the value is required, we are simply reusing the value that is already available. We are storing everything, d comma t is stored, the distance between A to D is stored. So, we are trying to utilize this existing value to find the resultant. So, this sort of approach is only we are doing. Then this is a different algorithm. This algorithm is called backward approach. The earlier algorithm was called the forward approach, where we are trying to see everything from the sink point of view and then we are trying to formulate the decision. But whereas here we are trying to go from the, we are going to view everything from the source point of view. So, the approach becomes backward, but the reasoning becomes a forward reasoning. So, in this particular example, you can see very well the approach is like this. The distance between S to A is noted down. Similarly, the distance between S to B is noted down. Distance between S to C is noted down. So, now we are trying to see from your source side what will be the cost required if I want to travel from S to D. You can see very well it is going to be the minimum of S comma A plus the distance between A to D. Similarly, I will see between the distance between S and B and B to D, only these two possibilities are there. So, it becomes something like 1 plus 4 and 2 plus 9. So, the minimum is 5. Then I want to explore this distance between S to E. One possibility is from S to A and then A to E, one possibility is there. Another possibility is from S to B and then B to E, one possibility is there. So, if you substitute the values, it is going to be distance between S and A, it is 1 plus A to E, it is going to be 11, comma 2 plus 5. So, the minimum is going to be 7. Similarly, you can find the distance between S to F. Again you can see very well there are two possibilities. One is from S to B and B to F. Another possibility is from S to C and then from C to F. It is going to be 7. Okay. So, now we have seen up to this particular stage. Next stage does not involve any subsolution. So, straight away we can go, it is going to be the minimum of reaching D from A. So, it becomes minimum of D of S comma D plus distance between D and T. This is one option. Another option is S to E and then E to T. Another is S to C and what you say S to F and then from F to T. If you substitute everything, you can see very well again you are getting a value of 9. So, now you can see very well again like your earlier algorithm, we are able to get the minimum path, that is going to be 9, and if you trace exactly what gave you the minimum, you can easily find out the distance. So, here you can see very well the minimum is going to be 7, here also 7 is there, but you can see very well if you take the minimum of the earlier stage, you can obviously make the difference of why we are not choosing what you say B and why we are choosing C. And if you try to see that, you can see very well the path becomes S to C, C to F and F to T. This approach is what we are calling as the forward reasoning, because we are seeing everything from the source point of view. And you can see the algorithm also. The algorithm looks something like this. Initially cost is going to be 0. Please note this particular thing. Now we are going in the from left to right. Therefore, the loop is also 2 to n do. Please recollect, in the last algorithm, since we are coming from right to left, we are starting a loop and then we are decrementing the loop actually by -1. But whereas here we are going from left to right, therefore, the loop becomes 2 to n do. Again we are choosing the minimum cost edge. So, let R be such that R comma j is an edge of G, and you can see very well we are going to update the cost and then we are going to record everything into dj, and the path can be easily obtained from the reverse actually, and this is the way in which the path can be extracted. So, now you can see very well we can use either the forward approach or backward approach. So, you can see very well, suppose if you formulate the recurrence equation in the forward approach, then the reasoning is backwards and vice versa. And similarly, if the relations are formulated using the backward approach, they are solved forwards. And we had seen that greedy approach clearly fails in this particular case. Therefore, we use dynamic programming only. The advantage of this particular dynamic programming is that we can also formulate the other problems also as the multi-stage graphs, and the same algorithm can be applied. So, this is the greatest advantage, and as a piece of advice I want to say that many problems in computer science can be easily modeled as problems based on this. So, now let me illustrate, demonstrate that how other problems can be converted to the multi-stage graph. You can see this particular slide. This slide already this problem already we had discussed. It is 0 bar 1 knapsack problem. Please recollect, we discussed this as part of our greedy approach. Can you able to recollect? We have n items, every item has got a profit. We have to see the capacity of the knapsack, we have to maximize the profit, and these are some of the items we have, right. So, now let me coin this problem as a multi-stage graph problems. So, now you imagine like this, you have a knapsack, I am having the first item. Now, I have only two choices, either I can put the first item into the knapsack, or I can decide not to put that item into the knapsack. Suppose if I put a knapsack, if I put an item into the knapsack, I am going to get a profit, otherwise I am not going to get the profit at all. So, now you can see this slide, you can see this problem can easily be converted into a multi-stage graph. Initially nothing is there in the knapsack. So, now you can take a decision with respect to x1. You can decide to place this item into the knapsack, or I decide not to place this item into the knapsack. So, now the item 1 is present in the knapsack. So, now I have to take a decision with respect to the second items. I can place or not place, this I have not shown actually, because the graph will become very big. Similarly, I can place a third one or not to place. So, if I keep on generating like this, you can see very well this becomes something like a graph, and if I connect everything by means of T, you can see very well this becomes a multi-stage graph where everything is stages. So, what is the aim of a knapsack problem? It is to get the maximum profit. So, that means now you can see very well this is just opposite of what we had discussed so far. So, we are going to find the maximum cost path. So, that means it is not the shortest path, but it is going to be the longest path of your multi-stage graph. In other words, instead of choosing the minimum, if we can choose the maximum edge out of that particular graph, we can easily rewrite the old algorithm that we discussed into algorithm that can positively solve the problem of the knapsack also. The algorithm, you can see very well, becomes something like instead of minimum, it becomes maximum. Okay. So, this is the easiest way in which you can write algorithm for knapsack. Similarly, I can give you another example. This problem is about the resource allocation problem. So, in computer science, the project manager has to decide about who is getting what sort of resource. I have given a small example where the projects are given, 4 projects are there, and there are 3 types of resources are there, and each of these represent the cost of allocating that resource to the project. Again, you can see for this problem you need not have to think about writing the algorithm. The problem can be easily converted to a multi-stage graph. The problem becomes like this. Initially, no resource is being allotted. Now, I can allocate the first resource, second resource, third resource, fourth resource. I can also make a binary decision of not allocating that resource. So, if you formulate a graph like this, again you can see very well this becomes what you say, a sort of a multi-stage graph, and by applying the earlier algorithm to this particular problem, we can solve this problem also. Again, we have to find the longest path from the source S to T, and like the shortest path algorithm, if you trace your k which gave you the maximum at every stage, becomes a part of your what you say resource allocations. Similarly, you can also see the traveling salesperson problem. Again, you can see that multi-stage graph is used to solve this problem by converting this problem into a multi-stage graph problem. Traveling salesperson problem is one of the most important problem in computer science. Again, it is going to be a graph. So, the problem is we have to start from one vertex, we have to visit all other vertices, and then we have to come back to your original positions. The restriction is that every node should be visited only once, and then your final thing should be the same vertex from where you have started. So, this is a sample graph and this is a cost matrix. You can see very well how this problem is converted into a multi-stage graph. Again, you can see very well you have a graph which has got multiple stages. Again, traveling salesperson problem is the shortest path algorithm, that is you have to find the minimum cost path, but only thing is you have to come back to the destinations. Okay. So, in other words, I can state that the advantage of dynamic programming is that once you have an algorithm, you can reformulate that problem into variety of categories, and many other problems can be categorized as varieties for which some of the standard dynamic programming algorithm can be applied to find the solutions. So, that is the greatest reason why this technique is so popular among mathematicians and computer science persons. Again, to reinforce this particular concept, I would like to illustrate a small problem called the binomial coefficient, and again you can see very well how the principles of dynamic programming operates here. Kindly see this particular slide. The problem of finding the binomial coefficient is by applying this particular formula. So, the formula is n factorial divided by k factorial and n minus k factorial, and if I ask you to write a program, the conventional way of writing the algorithm is maybe perhaps we can write a factorial program, and then we are going to call that, and then we can find the solutions. That is how the normal programs will look like. But since we are trying to solve this problem using the dynamic programming approach, we can reformulate this problem as a dynamic programming problem. You can kindly go through the slide actually. So, the slide says that your NCK can be restated as a recursive relation like this. Suppose if k is equal to 0 or k is equal to n, it is going to be 1, otherwise the problem is divided into a subproblem like this. A binomial coefficient is the number of combinations of k elements from an n element set. So, I am restating this problem as a recursive equation, and dynamic programming comes now because I am going to record the intermediate results into a table, and then I am going to reuse this table to find the final answer. So, let me start writing the algorithm. The first step is I am going to establish a recursive property, that is binomial of I comma j is going to be binomial of I minus 1 j minus 1 plus b of I minus 1 j, j ranges from 0 to I, otherwise it is going to be 1. So, this is going to be the first step. I was telling you that the greatest challenge in dynamic programming is to establish a recursive property. Once you identify a recursive property for a given problem, then your solution is going to be a cakewalk, otherwise it is not. Second thing is, once you formulate a recursive equation, all you have to do is you have to solve the problem in the bottom up fashion by computing row wise, by computing the rows in B in sequence starting with the first row. So, let me give you a small example for you. I want to calculate the binomial coefficient of 4, 2. This is what my intention is. See how dynamic programming is going to solve. Straight away it is not finding the binomial coefficient of 4, 2, but instead it starts like this. First it tries to find your row 0. So, it tries to formulate a table and it tries to find the first value of b of 0, 0, that is b of I, j. In the previous recursive property, we have seen that if I is equal to j or j equal to 0, then the value of binomial coefficient is going to be 1. According to this particular thing, you can see very well it is going to be 1. Then I am going to compute the next row. Next row is going to be b of 1, 0. So, b of 1, 0, again you can see very well, you can substitute into this, it becomes b of 1, 0, then it is going to be 1, 1 minus 1 plus b of 1 minus 1, and then j is going to be your 0. So, you can see very well it is going to be 1. So, by substituting these values of I, j into this particular recursive property, you can easily find the answers for everything. So, the next row is b of 1, 0, 1, b of 1, 1, it is going to be 1. Okay. So, now you can see the advantage of next thing. Binomial coefficient of 2, 0 is going to be 1 because j is going to be 0. Now you can see binomial of 2, 1 is binomial of 1, 0 and binomial of 1, 1. Binomial of 1, 0 already we have found it. Since already we found out, this need not have to be recomputed. So, I can simply reuse this value here. So, this becomes 1 plus 1, it is going to be 2, and b of 2, 2 is 1 because I equal to j, therefore, it is 1. Now, row 2 is over. Now, row 3 is calculated like this, b of 3, 0 is 1, b of 3, 1 is going to be b of 2, 0 already which we have computed as 1. Binomial coefficient of 2, 1 is also already we have found out, it is going to be 2. Therefore, you can see very well it is going to be 3. Similarly, b of 3, 2 is going to be 3. So, third row is over. Now, I can go on to calculate row 4. b of 4, 0 is 1 because j equal to 0. b of 4, 1 is b of 3, 0. This already we have found out in the earlier row. Now, we are getting b of 4, 2. This is what we are requiring for. So, now you can see very well b of 4, 2 is nothing but b of 3, 1 plus b of 3 comma 2, which is nothing but 3 plus 3, which is going to be 6. So, binomial coefficient of what is say 4 comma 2 is going to be the 6. You may ask a question like this, that is, our aim is to find b of 4 comma 2, but is it not a longer way of solving this? The reason is, I was telling you that in dynamic programming multiple sequences will be generated. Suppose if I have an algorithm, if I have solutions like this, if somebody else is asking me what is the binomial coefficient of 3 comma 2, I need not have to rewrite the algorithm, but instead I can simply refer to the table and I can give the answer for b of 3 comma 2. That is the greatest advantage of dynamic programming. In other words, I can write a generic algorithm for finding the solution, and as the process goes on, your intermediate table will be kept on increasing, and you will have many solutions that is present in that particular table, and later on if any requirement comes actually, so any different requirements comes, by referring to that particular table you can always generate the solutions. That is the greatest advantage of this. Second major advantage of dynamic programming is that guarantee. As I was telling you that it works on the longer term planning, therefore the solution will be more effective. The third reason why dynamic programming is very effective is that writing a program is very easy. These are manual calculations. That is why by looking at this, perhaps you may think that the dynamic programming is complicated, but if you are trying to write this as a program, this is a very easy task, because all you have is all you require is a recursive equation, and since that dynamic programming, the first step itself is creation of recursive equations, we can easily write program for this. Suppose if you ask me to write a program for this particular problem, my task is very simple. All I have to do is I have to take this recursive function and substitute that into the equations. Kindly see this table. You can see very well, every new row is generated by reusing the values of your previous row. So, you can see very well, your table keeps on growing. This is how your table will look like. In the previous problem, we are stopping with 4 comma 2 because it was the target. If you want, you can keep on going, okay. And as I said earlier, if anyone wants any answer for a particular thing, all you have to do is you have to refer to this table and then you can generate the solutions. So, now you can see very well the program aspect. I have the recursive equation. So, all I have to do is I have to convert that into a algorithm like this. For I equal to 0 to n, for j equal to 0 to, now you can see very well. Why we are giving a minimum of I comma k is that sometimes we may not wish to generate all the values of the table. Suppose let us say if my target is something like 4 comma 2, why should I generate value for 4 comma 3 and 4 comma 4? It is not necessary. So, it is better if we have the minimum requirement, so that the entire value of the table need not have to be generated. So, we are taking a minimum I comma k equal to do, And here what I am trying to do is that I am trying to take the recursive equation of your earlier case, and then I am trying to put everything into this particular table. So, now you can see very well the job of writing algorithm is very simple, because all I am doing is I am simply substituting that recursive equation into the program, and of course, you can see the analysis part also. So, if you try to see for different values of n, the number of passes it requires, you can see very well it comes approximately